how the mixture is prepared. It only depends on the initial and the final state. So this means that like even if the change can be written as a two equation, this should be the same. So this means that when the first gives us equation and the second one should be the same, so this part should be equal to 0. So we are gonna write the NAD mu A plus NB mu B is equal to the 0. And in the general form, we can write for the J component, and the sum of this all composition multiplied by the N and the chemical potential change should be 0. And this is the Gibbs-Duhem equation. So for our binary mixture, then we can write this chemical potential for the B component is minus NA over NB and mu A. So this means that the chemical potential change is not independent function, is always dependent on the other chemical functions. And this is also, they have opposite sign of different chemical functions. And also this Gibbs-Duhem equation can be applied to other partial molar quantity, for example, the partial molar volume. So this also can be written like the sum of Nj with J is equal to the 0. This can be also effective for this binary mixture as well. Show some example for this Gibbs-Duhem equation. Here in this example, experimental values of the partial molar volume of potassium sulfate in water at 298 K are found with the expression VB is equal to 32 again plus 18 x to 1 over 2. Where this VB is the molar volume of potassium sulfate. The unit is cubic centimeter per mole, and X is the numerical value of the molarity of potassium sulfate. This means that X is equal to B over B naught. This B naught is kind of standard value, which is 1 mole per kilogram. And what this example say, use the Gibbs-Duhem equation to derive an equation for the molar volume of water in the solution. To get what is the VA. And the molar volume of pure water at 298 K is 18 cubic centimeter per mole. Let's solve this problem. What this example said, the pure water molar volume is 18.079 cubic centimeter per mole. And then what is the mixture of what is the molar volume of water molar in the mixture. So from the Gibbs-Duhem equation, what we know is that dVA is equal to the minus and NB over NA dV. And we would like to know the VA, so we are going to integrate this equation. So that means that VA is equal to the VA star, which is the initial value, minus integrate the 0 to VV and V over NA dV. So we are gonna, if we integrate this one, we will get the VA. So here what we know is that VV is a function of X. So dVV is a function of, sorry, VV is a function of X. So if we differentiate the both sides, differentiate fx and fx. So what this means that VV is 9.108 x over x to the minus r. This is just a mathematics. So we know that what is the dVs here. We know the dVv here, and what is the NB over NA. So this is the end of how much more, the amount of mole for component D over the mole of A. But we actually don't know about these moles, but we know that this X is a function of the molarity. So we are going to change this one to molarity. Let's start here. Let's leave the NB. And let's think about this water. So NA means the mass inside the mixture divided by the molar flow. So if we calculate this one, we need to know the mole, so we can write this. And the definition of a molarity is the mole of a solid divided by the mass, solvent mass. So this means that the solute is B, which is a containing surface, and the solvent is water A. So MB over WA is the molarity B. So MB over NA is the B NA. And NA is 18 grams for water, for the molecular weight for the water. So I think we all know about unknown values. So let's rewrite this one. Here, VA is equal to VA star is 18. 9. We are going to integrate 0 to this is changed by the x. So VB also should change it to the x. Is over B. We're gonna here, right? This and A and B over NA is BNA and we are gonna just integrate this part. Let's see. This molarity. Yeah, and here actually B also can be written as x function. So here D over D naught is x. So B is D naught divided by x. So we are gonna write this x and a like this. Here. This will x on number 2. Then we can integrate this x and the rest of it is just a constant. So D naught is 1 mole per kilogram, and Na is 18 gram per mole. If we integrate the x to r, it is 2 over 3. Like this, and 0 is 0, and we are gonna insert this B over B naught over 2. Then we just can calculate the or calculate this constant, and the VA finally can be written as the function of just the molarity B. This V naught is also constant, which is 1 mole per kilogram. So if we rearrange, we calculate this one, VA is equal to 18.79 minus 0.1. Based on this VB equation, we can get this VA by the VB equation. Let's see the graph here. So this is a water line for the molar volume of water, cubic centimeter per mole. And this is a B, the molarity of this potassium sulfate. So if there is no potassium sulfate, if you use this axis, the initial volume is 18.079. But when you add this potassium sulfate, the water molar volume decreases, and this is the VA. But by this gives you an equation, VB has a opposite sign. So this means that when the water molar volume decreases, this potassium sulfate molar volume increases like this. So from here to like if the molarity becomes 41, this becomes around 38 cubic centimeters per mole. The relation between the volume A and volume B, so molar volume A and B, the liquid mixture, which can be calculated with the Gibbs-Duhem equation. So from this chapter, we are gonna learn about the thermodynamics of a mixing process. So at the constant pressure and the temperature, and the composition is constant, the Gibbs energy depends on this equation, mu A and A plus mu B and B for a binary mixture. And for a spontaneous change, this Gibbs energy should decrease as in the spontaneous mixing of two substances. For example, let's see the figure here, which is the example of a mixing process for the perfect gases. This is a perfect gas condition. Two perfect gases and the component A and B in a two container are mixed into the same container after mixing. So in this process, the temperature is the same, it's constant before and after mixing, and the initial state, the gas is in a mechanical equilibrium with the pressure P. But after mixing, the pressure P is constant. But because now the component A and B exist in the same container, so this pressure is the sum of the partial pressure of A and the B. So PA plus PB is the P, pressure. So let's talk about the Gibbs energy change for this process from the fundamental equation of chemical thermodynamics, dg with dt minus st. And here, this process is happening at the constant temperature. So this means that we can remove this SDT term. So the Gibbs energy depends on the pressure. So let's say that if we wanna get the Gibbs energy at some pressure, final pressure, means that sum of Gibbs energy at the initial pressure plus integrated from initial pressure to the final pressure with P. And we are going to consider the molar Gibbs energy because we also would like to know the chemical potential. So let's say that this can be changed to the molar Gibbs energy. Perfect gas, so which means that we can use the ideal gas law, so Vm, and be written R over P, and so this energy becomes write this here. And let's assume that like the initial pressure was standard tension, not which is 1 bar. This is just the assumption for simplification. And then let's say that we don't know about the final pressure. So we're gonna just write P final is equal to P. So we arrange this equation. Where this RG and the pressure P is standard is RG at the 1 bar. Plus RT Ln P over P naught. But this P naught is a 1 bar, so we can just write this equation like P. The P unit should be bar, because there was a P naught in this equation. So we just calculate this RG at the pressure P. And actually this molar this energy can be written as a chemical tension. So we can just rewrite this equation as the chemical tension, not So let's get back to the mixing process. So we are gonna calculate the initial phase. It gives energy for initial state, and it gives energy for final state. So this energy for initial state is in the picture. This is the initial state. The gases are separating. So Na plus is equal to the naught plus because the pressure is P in the figure. We just use this equation. And also it is applied to the molecule B as well. And after mixing, the pressure P is the sum of the partial pressure of A and B. So this should write Na U N naught T and PA. This is the partial pressure for A, and B naught T and where the partial pressure A plus partial pressure B is equal to the ratio, which is also same as the initial pressure. So what we would like to know that is how these changes during the mixing process. So we want to know that there can mix for each energy. So we are gonna get the final each energy. So you can see this will be removed, and the left sum is some kind of expression for the pressure. So we can write A R T and N P A and over P plus ND R T N PV like the partial pressure J is one fraction multiplied by the total pressure. So this can be expressed as the mole fraction A, meaning that A, C, also this component NA also expressed the mole fraction X multiplied the total amount of molecules. So this would be A, and this is X, E. Now we arrange this change of Gibbs energy. The NRT, A, and X, and plus XB, and N. So we make this equation as a simpler form. And what we know, what we can read from this equation, mole fraction is always smaller than 1. So this means that ln(x) is always negative. So that mixture for Gibbs energy always negative. Meaning that the mixing process for this perfect gas is spontaneous in all proportions. This is about the and there are some other thermodynamic mixing functions, for example, entropy and the enthalpy. Let's also derive this entropy and the enthalpy for the mixing process. So from the fundamental equation, S entropy S is equal to delta G over delta T while holding the pressure and other component constant. So we can derive this equation as a mix function. So delta mix for entropy is also equal to delta mix energy T, and delta mix Gibbs energy is a function of temperature, nRT multiplied something like that. So we just differentiate the function over T, then becomes minus and R and this A plus XB and N X. So here again, mole fraction is always smaller than 1, meaning that ln(x) is negative. But delta entropy has a minus sign, so this means that delta mixture entropy change is always positive. So this also indicates that this mixing process for two perfect gases is a spontaneous change. So the entropy is always positive. Let's see the enthalpy here. So by the definition, enthalpy is energy change plus the T multiplied delta S. So this is just the delta S was the differential of temperature over this energy. So if we just multiply temperature here, which is the same as the Gibbs energy change, So means the enthalpy is 0. So enthalpy mixture change always 0 for this perfect gas. So mixing process. But this means that there is no enthalpy change when two perfect gas that have no interaction are mixed without the volume change. So the driving force of mixing comes from the increasing entropy, like a matter is distributed, or from the decreasing its energy, not from its entropy. So you can see this graph gives us changing over the mole fraction. It is always negative, and for the entropy, it is always positive here. 한국어로 정리하고 그다음에 이제 나갈게요. 포지션에 의해서 변화가 되기 때문에 이런 식으로 디퍼런시에이션이 꼭 붙여줘야 되고요. 그런데 저번 시간에 배웠듯이 일정 압력이나 온도 조건에서는 이 딥에너지를 컴포지션이 변할 때 와 이제 케미컬의 곱한 값으로 표현을 해줄 수 있죠. 이거 보시게 되면은 이런 식으로 칼슘 몰라 볼륨을 구하고 이것도 이제 딥에너지에 적용하면 똑같이 되는 거죠. 포텐셜이 이런 식으로 정리가 되어지기 때문에 에너지를 바이너리 믹스처의 에너지를 이런 식으로 써게 되는데 그렇게 되면은 결국 이 두 개의 식이 반드시 서로 똑같아야 되는데 이게 믹스에너지가 상태함수이기 때문에 이제 이런 식으로 변화해서 만들어졌든 혹은 뭐 다른 조건에 의해서 믹스처가 프리페어 됐든 간에 이제 최종 파이널 스테이트가 같게 되면은 믹스 에너지 체인지가 같잖아요. 그렇기 때문에 이 두 개의 식이 반드시 동일해야 됩니다. 그래서 이게 이제 동일을 하려면 뒤쪽에 있는 부분, 그 케미컬 포텐셜이 변화하는 부분에 이 부분이 이제 다 0이 되어야 되는 거고요. 그래서 이거를 이제 일반화하는 거가 이제 기수 구현 방정식이라고 부르는 거고, 뭐 J 컴포넌트를 J 컴포넌트에 이제 N이랑 그 케미컬 포텐셜을 다 곱한 값은 반드시 0이어야 된다. 이게 이제 구현 방정식이고요. 이 식이 나타내는 바는 이제 혼합물에서 한 성분의 화학전이는 다른 성분들의 화학전이와 무관하게 독립적으로 변화시킬 수 없다는 건데 이제 결국 화학전이들이 모두 디펜던트하게 변한다는 뜻입니다. 하나를 바꾸게 되면은 이제 다른 하나도 반드시 변화해야 되는 그런 피직스가 여기 있는 거고요. 그래서 요거를 이제 바이너리 믹스처에 대해서 나타내게 되면은 d mu b는 마이너스 ml over nb d mu a 이렇게 나타내게 되는 거고요. 이제 마이너스가 붙어 있는 게 아까도 보셨듯이 이런 식으로 물에 몰라 볼륨이 칼슘 몰라 볼륨이 바뀔 때 포테시움 설페이트도 반대 방향으로 바뀌는 것을 확인을 했었고 모든 분모 소질에 적용할 수 있습니다. 그 다음에 이제 믹싱 프로세스의 서머다이나믹에서 배웠고요. 그래서 저희가 봤던 게 이제 완전 기체가 혼합 과정을 이루어질 때 이 깁스 에너지와 엔트로피, 엔탈피의 변화가 어떻게 변화하는지 변화에 대해서 이제 공부를 했고요. 그래서 이제 순수 기체의 화학 포텐셜은 압력에 의해서 바뀌게 됩니다. 아까 유도한 것처럼 이제 이런 기체의 화학 포텐셜 U는 스탠다드 케미컬 포텐셜에다가 압력이 얼마나 바뀌는지에 대해서 더한 값이 이제 우리가 원하는 어떤 프레셔의 어떤 certain 프레셔의 화학 포텐셜 되는 거고요. 맛은 표준 화학 포텐셜을 그리고 원바일 때 순물질의 기체가 나타나는 화학 포텐셜입니다. 그리고 만약에 이제 이게 혼합물이게 되면은 어떤 기체 J가 있게 되면은 그거에 대해서 그냥 쓰게 되면 이런 식으로 구분할 요동성에 대해 그 화학 포텐셜의 구분할 요동성의 식을 구할 수가 있겠죠. 그래서 아까 어떤 이런 이니셜 스테이트로 NAND가 존재하는 거가 이제 믹싱이 되게 되면은 이런 식으로 하나의 컨테이너에서 하나의 컨테이너에 들어가게 되고 그때에 깁스 에너지 같은 경우는 이니셜 같은 경우에는 NaUA 플러스 NB 이렇게 따로따로 있으니까 이런 식으로 적어줄 수가 있게 되고요. 그때의 프레셔가 지금 동일하기 때문에 P라고 적혀 있습니다. 왜냐면 세퍼레이트 되어 있는데 이게 메카니컬 이퀄리브리엄이라서 두 개의 프레셔가 지금 같은 상태입니다. 이제 섞이게 되면은 이제 동일한 프레셔가 나오지만 이 안쪽에 PA랑 안쪽에 A가 나타내는 partial 프레셔랑 B가 나타내는 partial 프레셔가 다른 상태가 되게 되고요. 그렇기 때문에 혼합 후에 총 깁스 에너지는 NaUA 플러스 RT, ln, PA 이때는 이제 partial 프레셔가 되는 거예요. 그때에 화학 포텐셜을 구별을 해야 되는 이거 마찬가지예요. 그래서 이 두 개를 뺀값이 결국 혼합 깁스 에너지 델타 믹스 깁스 에너지인 거고 그거 같은 경우에는 nRT, nPA over 플러스 nBRT, nPB over P. 그래서 partial 프레셔를 토탈 프레셔로 나눈 값이고 이거 같은 경우에는 챕터 1에서 배웠다시피 이제 몰 분율을 이용해서 표현을 할 수가 있게 돼요. 그래서 이제 혼합 깁스 에너지를 이제 간단하게 써보면 nRT에다가 XALN X를 곱하고 이것도 이제 더한 값이 혼합 깁스 에너지가 되게 되는 거고요. 이 몰 분율 같은 경우에는 언제나 1보다 작기 때문에 ln X, ln B가 모두 0보다 작죠. 그렇기 때문에 이제 혼합 깁스 에너지도 언제나 네거티브 상태가 돼요. 이 뜻은 이 이상 기체의 혼합 과정이 spontaneous change다라는 것을 나타내고 있고, 그리고 이제 엔트로피나 이제 엔탈피에 대해서도 고려를 해보면은 엔트로피 같은 경우에는 델 G over 델 T 프레셔와 이제 other 컴포넌트들을 콘스턴트 할 때 이제 변화가 이제 엔트로피 변화인 거고요. 그래서 혼합 엔트로피 변화는 결국 이 깁스 에너지 믹스처를 T로 나눈 값이고 요거 같은 경우는 NR, XN, NX 플러스 XB, NX 여기 이제 항상 마이너스 사인이 이렇게 되고요. 여기서도 이제 X, 그러니까 몰 분율이 언제나 1보다 작기 때문에 LNX는 언제나 네거티브이고 그렇게 돼서 이 혼합 엔트로피도 언제나 0보다 크게 됩니다. 그래서 이제 이거 또한 엔트로피가 증가하는 방향으로 진행되기 때문에 믹싱 같은 경우에는 언제나 스폰테니스 리액션이다 라는 하는 거고요. 그 다음에 엔탈피에 대해서 고려를 해보면은 엔탈피 같은 경우에는 깁스 에너지 플러스 T 델타 S잖아요. 그리고 우리가 주황 이걸 해보면은 이 혼합 엔탈피, 그러니까 믹싱 프로세스 오브 퍼펙트 가스의 혼합 엔탈피는 언제나 0이 같은 경우는 이 기체 혼합물이 퍼펙트 가스니까 이제 분자 사이에 상호작용이 없어서 그냥 에너지가 변하기 때문에 하나의 0이게 되고요. 그래서 이제 드라이빙, 그러니까 이 혼합을 푸시하는 드라이빙 포스는 이제 엔트로피가 증가하는 방향 혹은 깁스 에너지가 감소하는 방향이라고 보시면 됩니다. 그다음에 이제 액체의 화학 포텐셜에 대해서 공부를 하겠습니다. Properties of a liquid mixture. It is necessary to know how the design of a liquid varies with the composition. So we are going to use the fact that at the equilibrium, the chemical potential of vapor is equal to its chemical potential to the liquid. What this means is that let's think about there is a closed vessel and there is a pure substance A, liquid, and there should be a vapor of A. And in the equilibrium, the chemical potential of a liquid and the vapor should be same. So we are gonna add the star here, which means that this is the pure substance. So the pure substance, the vapor pressure of the pure substance A is a P star, and this chemical potential is equal to the pure substance A liquid chemical potential. So these are the same. But if we add the solute B here, now the system has two components, a liquid, let's say liquid mixture, B liquid, and because of the V, there should be a gas vapor B as well. But in this case, if the system is in equilibrium, the chemical potential A is always same. So here we're gonna just make the chemical potential A gas phase at the pressure. So this is the vapor pressure for this mixture is equal to the chemical potential A at the liquid. So here we want to know that this chemical potential of liquid in the mixture. So we are gonna use the this equation here. We get what the chemical potential for gas, which is mu is mu naught plus RT LMP here, this one. So we know that this chemical potential from this equation. So this is the same as the chemical potential for pure substance A at the liquid phase, and we are gonna write this one as plus RT and N P star. This equation is for this one, and let's see this case as well. So we also know this one, this chemical potential for vapor A. It's in NA. So the chemical potential A at the liquid phase is same as the chemical potential vapor, which is mu A naught gas plus RT and N. The standard chemical potential is the same because it is the 1 bar. So we can replace this standard potential by this equation. So this becomes mu A star liquid plus minus RT and then base. for pure substance plus RT and PA, which is the pressure, vapor pressure in the mixture. So we write this equation. And by the experimental observation, the scientists discovered that this vapor pressure ratio, like the vapor pressure for the mixture, the vapor pressure for the pure solvent A is one fraction of A. So this is for the just the experimental observation. It's not from the theory. So this condition is can be applied to a certain situation, like when the solution is ideal solution. So finally, this liquid potential A can be represented So interestingly, we derive this equation from the gas phase, but the last equation there is no gas here. So this means that the vapor, actually we assume the perfect gas, but it doesn't have to be the perfect gas for this equation. So there is only liquid potential and the liquid vapor potential for pure substance, and this small fraction is in the liquid mixture. Not in the gas phase. So as I mentioned, the ratio of vapor pressure A over this vapor pressure for pure substance can be expressed as a mole fraction, which is a Groth law. And the ideal solution, this is a solution where all components obey this Raoult's law throughout the combustion rate, meaning that actually real solution does not follow this Raoult's law. Then the question is that we just calculate for the solvent A, so we also know what is the solute. So we are going to assume another condition. Let's say that what if we have a non-ideal solution, but nearly ideal solution, like such as a real but dilute solution. So Henry's law is scientists found experimentally. This is also experimental observation for real solution at the low concentration. The constant of proportionality is not the vapor pressure of the pure substance, but some empirical constant K, which is the Henry's constant. So by the Henry's law, unlike this Raoult's law for solute, the vapor pressure of solute B is multiplied by the mole fraction and then some empirical constant, means that it is decided by the experiment. So So this ideal dilute solution means that the mixture, the solute, is very dilute, obeys the Henry's law, and the solvent A obeys the Raoult's law, like this condition. There are some examples of Henry's constant. And for practical application, Henry's law expressed in terms of molarity B of the solute. The molarity is the molar amount of solute over mass of solvent B. So it is written as a Pb is equal to Pb of Kb. And also this is a dimensionless property, and this is a pressure. So the unit of Henry's constant is pressure, like bar, atm, or Pascal. And let's see this graph here. So when the mole fraction of B, the solute B is very diluted here, the pressure, the real solution pressure follows the Henry's law. But when it is the too concentrated, moderate concentrated, there is a deviation from the Henry's law and the Raoult's law as well. But actually, at the extreme condition, Pb is like becomes the ideal solution because it is a pure substance B. So at the mole fraction of B, kind of pure solvent, so it follows the ideal solution like a Raoult's law. 네, 여기 다음부터는 다음 시간에 수고하셨어요.